That's why.
Morning. Where did he go?
He's hiding right here. He doesn't like your loud, annoying self.
No, good pop, you're gonna get terrified. He literally jumped up so high, trips like this, he falls on his back. Oh, he was so tiny though. No, it's tiny. Do that again, so sweet, take a video. Yeah, it was very tiny in that house.
I have a video of you throwing snowballs at him outside and he's trying to catch the snowballs, but he bites them and they just explode. I was just about to text you and say, did you see? She called and I just clicked the hang up button and then she called a second time and I thought, okay, there's an actual problem. So okay, careful. Oop, okay, guys, don't play with the bowl on the table. We're good. And so I picked up and she told me what was up and I was like, yeah. All right, thank you for rescuing her. All right, she's a mess. Ashley's brakes died and she's stuck. She called in the middle of my first class and I was like, it's Tuesday and you never call unless there's an emergency, so what's up? Well, all right, let me pass some out. Pass back some papers so we can get going. Otto, you're fine. The boy Otto, she'll be back. Here. In this time, okay. Somebody may want to help her with this leg too then. Chloe's still over there. James is still over there. All right, come on in and get ready. Yes. Do what? Oh, that's odd. That's my mom. He's very attached to my mother. When she leaves, he's like totally lost. Yeah. Yes. Oh, you put it on the counter. Thank you for bringing that down. We walked up at the right time.
I'm assuming the trouble with the thing.
Let me go the other way. I'm like, wait a minute, you're usually right here. And again. Oh, great. You can just get around the counter. Thank you. Thank you for doing that.
Is that also double?
Huh?
Yeah. I don't kind of move all of the house across the desk.
Puppy counts as a dog when that's like a dog.
I wanted to see what this one
Yeah.
Oh, that's famous.
Chucky, that's hard. How did we standing on top of a bunch of gears and a couple of glasses and possible things?
Yeah, it's my mom. That's Otto.
Really?
Accurate.
Yeah, his foot is in his. Put in those hot wings. He enjoyed it.
He's very old and spoiled rotten. He's, I don't know, he went somewhere. All right, people. Okay, are we all about ready? I'll let you guys get yourselves situated.
Opening scene of Star Wars.
Maybe it's a little Star Warsy, I don't know, could be. Mm-hmm.
Where is it?
Hold on, it was, had to time it. My timing changed.
Like that.
It's good.
Uh-huh.
It always looks weird in this, when you see it like this, but, all right. So this lesson, I'll tell you straight ahead, this lesson is definitely a shorter one because there's just not as much covered. But, that's okay, because we had a lot of talking about stuff for lab, and it's a good time for you guys to like make sure you've shared your information. Everybody has good, complete answers to study. Yes, sir.
Is there a Luke Skywalker out this time?
There might be. There just might be. You will have to wait and see. Make sure I have these out. Okay, so.
Everyone started singing.
All right, everybody. This is like when we play Jeopardy and everybody goes, "Da-na." You what? Yeah. All right, here we go. Everybody good? Everybody good? Everybody has sung all they're gonna sing for now. All right, so, right. Alrighty, so we're talking about forces today. Forces. So may the forces be with you, of course, right? You gotta have that. You know that on May 4th, that's what you say, right? May the forces be with you. Yep, may the force. Yep.
Why is one of them holding a spring?
It's the top of a lightsaber or something. You have to give AI credit for even knowing how to make a Jedi rat. So, you know, some of these are, I'm telling y'all, my favorite thing is Lab 11 is my favorite yet of all the AI stuff. It is super cool.
11 lab?
Yeah, it's going to be fun. It's going to be a lot of fun. All right. So first, let's talk about electromagnetic forces. This is not the last time we're going to talk about electromagnetism, but this is the first time we're going to introduce it. So electromagnetic forces. Oh, I've got Star Wars quotes in all of these. There we go. So electromagnetic forces are associated with charged particles. What do we mean when we're talking about charged particles? What you think, Colin? Ions. What's an ion?
A charged particle.
Mm-hmm.
Well, with a positive charge.
Or negative. And what exactly is it? What do you mean by particle? What particle is it?
Atom.
It's an atom with the charge. How would it get a charge?
By losing or gaining electrons.
Very good. By losing or gaining. What's those of you who've been with me before, what's an anion? Bailey?
Negative.
Yep. And how do you remember that an anion has a negative charge? Because it's, you think of it like an onion. There's an onion there.
That's the opposite of
It's a terrible, yeah. So what's the cation?
the positive one.
Positively adorable, right? So you can remember that your cations are positive and your anions are negative. So you're right. Charged particles, or sometimes just electrons. Just free electrons. So electric force and magnetic force are the only forces that can both attract and repel. I'm gonna say that again because it might show up on a test. Electric force and magnetic force are the only forces that can both attract and repel. Can anybody think of an example of how we use magnetic repelling force? Like, can you think of an example that you may have seen that we put it in action somehow? Let me think. Can you think of one, Jordan? Did you think it would?
Japan has floating trains. They do
Yes.
that using opposite.
Yes. Okay. So they're called maglev or magnetically levitated trains. Anybody ever been on a maglev?
No, but it sounds cool.
Yep. Drew, where were we on a maglev?
China.
In China. We took the maglev from Beijing, where our friend lived, not Beijing, Shanghai, where our friend lived, to the airport in Shanghai. Do you remember how fast we went?
No.
Somewhere I have a picture of it, but it was like, it was without a doubt the fastest we've ever traveled in our lives and probably will ever travel again. It's crazy. Why is it so fast?
It's really fast.
Why?
There's no friction.
There's zero friction. Yeah. So there's no friction because you've got this entire heavy train levitated above a track because it's being repelled. And the magnetic force is just enough to levitate a train. How did they make it move forward?
Yes.
No? Do you know?
They tilted the magnets.
It's a good thought. Do you know, Asher?
I think so.
Okay.
Don't they have a magnet at the back that's
Mhm.
also repelling it, so it's moving it forward?
Yeah, kind of. So it depends, but I think in general, they're using the magnetic force to move it along as well. Like there would be positive in the front that's pulling it, and as it moves along, that positive will switch to negative, which keeps it levitating. So,
I want to keep it on the track.
it's a track like any other. You know, it has like a, you know, it like locks around the track, but it doesn't sit on it like our trains here that roll on wheels do. It just floats. And it's crazy, crazy, crazy fast. And obviously, you can think of, you know, repelling and attracting forces, magnetic retracting forces. I mean, if you have a refrigerator at home, you probably got a magnet on it, right? What were you going to add, Lucas?
I just have a question.
Yeah.
Is it faster than the Nimbus 2000?
Definitely. It was very, very fast. Did you have a question too, Xander?
Is it faster than a plane?
No, I don't think it's faster than a plane, but it's super fast. Colin?
Fun fact, if you guys ever want a cool podcast, go listen to 30 animals that made us smarter. I
Ah,
was talking about how there was a problem with the maglev trains where as they were coming out of a tunnel, there was loud sonic booms with all the air.
Oh, yeah, pushing it through.
And so they redesigned the front of the train after a kingfisher's bill, which was specifically designed to cut through the water out of the
Very
shadow of
smart.
the fish, and that solved the problem.
Very smart. Yeah. Anybody else a podcast junkie? I'm a podcast junkie. Yeah, half the time I got at least one earbud in because I
Same.
like the true crime ones, but I will say if you like sciencey stuff, there's a really good one called Ologies. Actually, I saw a girl the other day wearing an Ologies t-shirt. And I was like, oh, it's a great podcast. But anything that's an ology, anything you can study, stuff you've never even heard of, they have an episode on it. And the host finds an expert in whatever that ology is, and that expert talks all about it. And it's fascinating. You wouldn't think there'd be so many things that are actually interesting.
I have a question. about
Mm-hmm.
that. Do they have one on Oreo?
They might have one on Ore. Are you an Oreologist?
And then
Is that would be the term Oreologist? I don't know. All right, so for our first one here, opposite charges attracts, like charges repel. What am I looking for here, Lucas?
Charged object.
Yeah, there you go. Okay, so we're looking for electric force in general. This is our definition. All right, so electric force is opposite charges attract, like charges repel. When an object loses electrons, it becomes positively charged and creates static electricity. Oh, it's just about that time of year, isn't it? Yep. Usually we get most of the static in the winter. Why do you think that is? Why, PJ?
It's colder.
Yeah, it's colder. What else changes, Tasha?
molecules are gonna. That's not very nice.
Well, some of it has to do with like what you're wearing. Like in the winter, you tend to be wearing a lot of stuff that is rubbing against the air and the floor and all that other stuff.
Woolen.
What now?
Woolen.
Yeah, woolen clothes. Yeah, for sure. So that creates static electricity. And we will talk more about electricity. We're going to do a whole bunch of experiments with electricity. We're going to create a little kind of like a miniature telegraph, and I'll teach you guys how to use our real one because we have the real one, right? And actually, I might even throw in some extra credit opportunities with learning the Morse code to tap out a message and understanding a message on the other side. I got books on it, but you can look it up. So if electric force is this first one, then what's the second one obviously going to be, Caitlin? There we go. Magnetic force, opposite poles attract. So it's charges when you're talking about electricity and poles when you're talking about magnets. All right. How do I phrase it? Okay, so you've got magnets that face north and south, right? You've got a north end and a south end on a magnet. That's what you call it, a north pole and a south pole. Which way does the north pole on a magnet want to go? PJ? You know, wants to go to the north. Yeah. Okay. Sort of. South. Okay. The north wants to attract south. Yeah. Kind of the, yeah.
Earth's magnetic poles are actually flipped, so
There you
the
go.
south pole is in the geographic north.
Right. Has it always been that way?
No.
No. Earth has flipped multiple times. The poles have switched. How do we know? Somebody from last year. Bailey, how do we know? Yeah. So go ahead, Yusuf, can you expand on it?
Yeah, because they make marks on the rocks.
They kind of make marks on the rocks. Yeah.
And like the mantle
Mhm.
is moving around, and therefore the core, which generates the magnetic core, is also magnetic field is also
Yeah.
rotating around.
Yeah.
That's why the magnetic poles are constantly moving.
James?
magnetic filaments
Mhm.
align themselves differently.
There you go. Okay, so yeah, so it's called magnetic striping. Oh no! Can you see him doing someone? Oh, here comes Ozzy now. Oh, I know, Bart. Something must be happening. Anyway, so yeah, so at the bottom of the seafloor, I'm sure, most specifically, right through the middle of the Atlantic Ocean, you've got seafloor spreading, which is due to convection currents within the mantle, like Colin said. And your seafloor, it's a divergent boundary, right? So it's moving like this, which means you've got magma coming up, cooling, becoming seafloor, and spreading out. And the reason we know that happens is because there are iron particles within the rocks, and they will orient themselves towards whichever pole based on how they're, whether this is north and this is south, and they'll go south north, they'll attract and repel appropriately. And then when the poles swap, you can look at the seafloor and see the magnetic, the opposite, the iron particles going in the opposite direction. So it actually kind of looks like it's mirror image. It's like this stripe and that stripe and this, and they're different widths. If you were to look like different, because sometimes it's a longer time before the poles switch and a shorter time. So yeah, so that entire concept proves both that we've got plate tectonics in motion and that we've also got magnetic poles that have swapped. We can see it. All right, so here is this Earth magnetic pole thing, and hopefully it's not going to kick me out. I think we've had some internet issues today. I blame the construction. I'm going to blame everything on construction until it's done, which will probably be 20 years from now. Just so you know, be prepared. Makes me crazy. It's craziness.
Or the electromagnetic force is one of the four fundamental forces of nature. It generates light and energy and holds atoms, matter, and the world as we know it together. Electromagnetism is a branch of physics that studies the interactions between electric and magnetic fields. All matter has an electric charge, which can be positive, negative, or zero. Opposite charges attract, while like charges repel. These electric forces bring and hold atoms together. And when atoms gain a positive or negative charge through the transfer of electrons, a measurable electric field will form. If those electrically charged particles start to move, the field will become a flowing electric current and form a magnetic field around it. Under the right circumstances, interacting electric and magnetic fields can continuously produce and sustain one another. This generates an electromagnetic field that transmits waves of electromagnetic energy or radiation into space. The intensity of this radiation is determined by its frequency. These frequencies make up what's known as the electromagnetic spectrum. Near the middle of the spectrum is visible light, such as light emitted by stars, fireflies, and computer screens. On either side are invisible electromagnetic waves. On one end are long, low-frequency radio waves that broadcast television and radio signals. Microwave
Yep. Don't come on, internet. Neat, 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 neat. Pizza, yum,
that
not
carry
microwave.
telephone signals and cook food, and infrared waves emitted by fires. On the other are short, high-frequency wavelengths, ultraviolet, X, and gamma radiation. Unlike low-frequency waves, these waves can pass through the human body, making them useful for medical applications. While electromagnetism has daily applications, it's also the engine that drives the planet as a whole. Thousands of miles below the Earth's surface, a layer of liquid metals churn and flow. This generates electric currents that then produce magnetic fields that all together encompass the entire planet. Called a geodynamo, this process causes Earth's poles to attain positive and negative charges, turning the planet into a giant electromagnet. This phenomenon also creates a protective layer around the planet. It shields us from the most harmful radiation in space, leaving us to enjoy a world held together in the strange and fundamental force of electromagnetism.
So that's going to be our first of what we call universal forces. First question on this, just real quick. They mentioned microwaves. How does a microwave actually work? Yeah, he's cool, right? But how does a microwave actually work? Like, what's it doing? It's passing those waves through. Yeah, but what's going on? Uh-huh.
It emits heated radiation, which in turn cooks food.
So if you were to reach in there, though, it's not warm like an oven where you've got convection heat that's radiating, right? It's radiant heat because the heat comes from the heating element. But if you put your hand in the oven, it's warm. How come when you put your hand in the microwave, then it's not warm? So here's what the microwave does. And this is here's your electromagnetic forces again. So it talked about how it's a long wave, right? So it's not going to pass through your body. It's like a radio wave. That's why they can't hurt us, right? So what it's doing is it's actually, do you know?
So in the oven, the radiation heats up like the heating elements.
Right.
Then the heat then radiates away from those, and that heats your food. In the microwave,
Mm-hmm.
it just shoots the radio waves directly into the food.
So kind of. So what it's doing is this. Do you know, Drew?
It will take the water molecules and cause them to shake, which will
Mm.
create friction,
Yeah, when you use a microwave, your food is friction heated. So basically what a microwave does is it rapidly swaps the poles. So all of the water is a bipolar molecule, right? Water will be attracted one way or another. So it's basically like it turns the water molecules this way, and then this way, and then this way, and then this way. And all of that quick switching back and forth creates friction, which heats your food. So when you use a microwave, you're just heating up your food with friction. It's just odd, but it's a really, really interesting technology. And I honestly, that was one of those ones where I go, who thought to do that? Like that's, yes.
That is the best rat ever.
The best rat ever? You like this rat?
That's why it's the best.
This is your friend Lucas. Okay, so the force is strong with this one, it says. So two forces, strong nuclear force and weak nuclear force, act within the nucleus to hold it together. So what's the first one we're talking about? All right, I'll go Xander.
Strong nuclear force.
Strong nuclear force acts on neutrons, protons, and it works over, that's to say short distances. Got to fix that one. So short distances. All right, and Milo, how about the next one? Yeah, obviously, that's going to be our weak nuclear force, and it allows for nuclear decay, and it goes shorter distances. So what's this thing at the bottom? The fundamental building blocks for particles such as protons and neutrons. What do we call these subatomic particles, Bailey? Quark. Okay, quark is a subatomic particle. If you were doing physics, or you're going into like, oh gosh, I don't know, any of those like super quantum physics, you start talking about quark, and quarks aren't the only ones. There's all kinds of little subatomic particles. Yeah, gluons. All right, did you have something else, Lucas?
It says acts on neutrons, protons without a comma or an and.
Acts on neutrons, comma, protons, comma, and yeah, I said it should say and short, not sort. Yeah, that's a typo right here.
But there's no comma after neutrons.
Oh, I see here.
Yeah.
Ah, okay.
brownie points.
All right, you got one. There you go. Yeah, this was a bigger one, but all right, yeah. So we have our little Darth Vader rat here. The force is strong with this one, but the nuclear forces are really they're not as strong. You would think they would be because they're kind of holding everything together. So this dude is going to explain strong, and then we have another one that's going to explain weak, and it's good because he's got good visuals, so you can see it better and understand it a little better.
If you're interested in learning about particle physics, one of the key topics you need to understand are the forces that come into play. For instance, we know of 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Of these 4, we have at least a little familiarity with gravity and electromagnetism. So naturally, I want to tell you something about the strong nuclear force. The first question you might want to know the answer to is, how do we know that there's a strong nuclear force at all? Well, this is something we've known for essentially a century. In 1911, Ernest Rutherford discovered the basic structure of the atom, which is that it consists of a small and dense core of positive electric charge called the nucleus, surrounded by a cloud of negatively charged electrons. And in 1917, he discovered the proton, which meant that the nucleus consisted not of a big blob of electric charge, but of a whole bunch of smaller blobs held together. Remember that each proton can be imagined as a tiny ball with a positive electrical charge. They say that opposites attract, and that might well work for couples, but it's definitely true for electrically charged particles. On the other hand, like charges repel each other. So let's imagine a simple nucleus consisting of just 2 protons. Since each proton has a positive electrical charge, they push each other apart. And they don't push each other apart a little bit. The repulsion force is about 20 pounds. 20 pounds is the respective force in the world of you and me. And the particle world is huge. It's so big that if you let the 2 protons go, they push until they were moving away from one another at a speed of over 8,000 miles per second. And I just picked a simple case of 2 protons. In the case of uranium, there are 92 protons all packed together in a ridiculously tiny volume. And a proton on the surface is repelled with a force of just over 70 pounds. So if these protons are all getting pushed apart from one another, what keeps them together? There's only one possibility. There has to be a force that is even stronger that counteracts the electromagnetic repulsion. And the name for that force is, you got it, the strong force. What do we know about the strong force? Well, we know that it's strong, and it can't just be a little stronger than the electromagnetic force. That's because if the 2 forces were pretty similar, it would be easy to knock protons out of the nucleus of atoms. And we know that's not true because nuclei last for millions and even billions of years. So the strong force has to be way stronger. From tests, we know that the strong force is about 100 times stronger than the electromagnetic force. But the story is a bit trickier than that. After all, if the force is so high, what keeps the strong force from continuing to gather protons until the whole universe consists of one big nucleus? If we look at the periodic table, we see that the highest stable element has no more than about 100 protons in it. And yes, I know the nuclei also contains neutrons. That doesn't change much in what we're talking about here. So it seems that with more than about 100 protons, the strong force can't hold it all together. What's that all about? It turns out that there is a property of the strong force that is quite different than the electromagnetic force. Electromagnetism has an infinite range. In principle, 2 electrically charged particles will feel a force between them if they're separated by the entire universe. Okay, the force would be small, but in principle, it's true. In contrast, the strong force is more like a contact force. When 2 protons touch each other, they feel a strong force. Pull them apart a little bit, and the strong force goes to 0. In a way, the strong force is a little like Velcro. When 2 pieces of Velcro aren't touching, the 2 pieces feel no force toward one another. So that's the strong force. It is stronger than the electromagnetic force, but it has a much shorter range. And those 2 properties explain why low-mass nuclei are stable and heavy ones aren't. In the heavy ones, all the protons in the nucleus push against all the other protons, while the strong force only feels the force of its neighbors. And this is all pretty cool. What I've told you here is actually nuclear physics, not particle physics. I'll make another video that brings the strong force into the particle. The strong force is a
Whoop. I didn't hit your button. Sorry. Keep going, sir.
fascinating subject, and it is the strongest known force in the universe.
Yeah.
Well, second strongest force.
He's strong. Super strong man. Okay. So that's strong. So here's the same guy doing weak. So you can compare them kind of together, apples to apples, because it's the same guy. Apples to apples.
Traditionally, scientists say that there are 4 fundamental forces in the universe. Actually, that number is fuzzier than you might think, and the more that I think about it, there's probably a video of that. But let's stick with tradition for now. The 4 fundamental forces are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. I've made videos about the first 3, but haven't really addressed the weak nuclear force. I saved the weak nuclear force for last because, well, in many respects, it's really mind-blowing and exhibits behaviors that are completely shocking. For instance, it's the only force that is aware of the spin of the particles involved and whether they are matter or antimatter. So how does that work? Well, to understand that, you need to know something about subatomic spin. In the classical world, spin is pretty easy. You spin an object around an axis, like you see me doing here with this ball, and you can spin it one way or the other. Now, scientists can define a direction for the spin, which is a little counterintuitive. The direction for the spin is along the rotation axis, but there is an ambiguity. After all, the axis extends both above and below the object. So, to break the ambiguity, you can take your right hand. By the way, it's important that you use your right hand.
Downstairs.
And let your fingers wrap in the direction that the object is spinning. And the direction of your thumb is the spin direction. In fact, once you've done that, you can kind of ignore the idea that the object is physically spinning at all and just rely on the direction of your thumb. And simplifying a little bit more, you can replace the thumb with an arrow. The direction of the arrow contains all information about the spin of the object. In the classical world, the length of the arrow depends on how fast the object is spinning. A faster spinning object has a bigger arrow, and a slower spinning object has a shorter arrow. In the subatomic world, these classical ideas aren't strictly correct, but they're still somewhat useful. The direction of the spin of an object can be represented by an arrow, and the length can represent the amount of spin. There are definitely major differences between classical and quantum spin. For instance, quantum objects don't actually spin. In addition, the spin axis has to be parallel or anti-parallel to the direction of motion. This is obviously not true in the classical world, but, well, the quantum world is very counterintuitive. Also, in the subatomic world, particles like electrons and neutrinos can have only a spin of plus or minus a half. The plus or minus half is used to indicate whether the thumb of the spin direction is in the direction or opposite the direction of the particle's motion. Things get even more complicated if the object isn't moving, but in the case I'm about to talk about, that particular situation isn't relevant. So in the 1950s, scientists had tested interactions using both the strong force and electromagnetism and had shown that neither of them cared a hill of beans about the direction of the spin of the particles involved. However, in 1956, 2 Chinese theoretical physicists, Fengdao Li and Chen Linyang, dug through the literature and found that nobody had tested whether the weak force cared. Now, neither of these guys knew how to test this because they were, well, theoretical physicists. So they turned to a female experimental colleague by the name of Chen Qiwu. The female thing will be relevant in a moment. Wu was an impressive scientist. She was the best in the business when it came to studying the spin of atomic nuclei. So what she decided to do was to set up an experiment in which cobalt-60 would decay via the weak force into nickel-60, an electron, and an electron antimatter neutrino.
Yeah,
in order to test
right?
whether the weak force cared about spin and spin directions, Wu had to set up a very strong magnetic field to align the spin of the cobalt nuclei. Spin is one of those things that is conserved, which means that it has to be the same before and after an interaction. The spin of cobalt-60 is 5, and the spin of the form of nickel-60 into which it decays is 4. The spin of both the electron and neutrino is half. So we can see in this diagram what has to happen in terms of spin. We can even put in some plus signs and an equal sign to really make the point. In terms of the decay, what you'd expect to see is that during the decay, the electron and antineutrino would fly away along the direction of the spin of the cobalt nucleus, or the opposite direction. And if the weak force doesn't care about spin, the electron moving up and antineutrino moving down configuration would occur as often as the electron down and antineutrino up configuration. Because it's very hard to detect neutrinos, she just looked for the direction the electron flew. So what did she see? Well, she saw the most unexpected thing. The electron always flew away in the direction opposite of the spin of the cobalt nucleus. Because momentum is conserved, that meant that the antineutrino always traveled in the other direction. So what did it mean? It meant that the weak force had a preference for certain spin configurations. After some thought and careful study, what we now know is Wu's observation originates from a very peculiar property of the weak force. This feature is the following thing. There's a very strict rule about the spin of neutrinos and the direction they're traveling. The rule is that the spin of a neutrino is opposite the direction the neutrino is traveling, and the spin of antineutrinos is parallel to the direction they're traveling. We physicists have a jargon for this sort of situation using hands. Take both hands and point your thumbs in the direction the particle is moving. If the fingers of your right hand curl in the sense that the particle is spinning, we say that it's a right-handed particle. If the fingers of your left hand curl in the direction of spin, it's a left-handed particle. And you can see here how the right-left-handed jargon is related to the arrow method of labeling motion and spin directions. Okay, now we're ready to talk about what this all means. An incautious individual would say that Wu found that all neutrinos are left-handed and antineutrinos are right-handed. But that would be a hasty statement. The more accurate statement is that since neutrinos are only observed via weak force interactions, we can say that the weak force only interacts with left-handed neutrinos and right-handed antineutrinos. And generalizing further, the weak force interacts with left-handed particles and right-handed antiparticles. So this is a big deal. The other forces don't care about the handedness of the particles they interact with, but the weak force does. This discovery blindsided the scientific community and required them to entirely rethink the theory of the weak force. It also raises the question of right-handed neutrinos. Do they not exist? Or do they exist, but we just can't see them because the weak force refuses to interact with them? The story of the search for right-handed neutrinos is an interesting one and worth a video in and of itself. If only there was someone with a history of creating videos about particle physics who could make it. And about that female thing, I sketched out the most basic description of Qiansheng Wu's experiment, but the reality was unbelievably subtler and more complex. It was an experimental masterpiece. Plus, the result overturned our understanding of the weak force. If you're a serious student of science history, it's worth looking up. With such an accomplishment, you'd think that she'd be a shoo-in for science's highest honor. And indeed, the 1957 Nobel Prize in Physics was awarded for this line of work to, you got it, Yang and Li. Wu's entirely overlooked. Now, I wasn't on the committee at that time. In fact, I wasn't even born. And maybe the committee had a strong bias for theoretical instead of experimental work. But I can't help wonder if gender didn't play a role. Maybe not, I don't know. But there is no question in my mind that Wu should have received part of that Nobel Prize. Anyone who could revolutionize our understanding of the universe as much as she did is simply a magnificent scientist.
Head started hurting.
Yeah.
Yeah, right? That was complex stuff, like super complex stuff. But it's interesting. It just gives you sort of a broad perspective. We're not going to get too nitty-gritty in this class. Who else when you think about somebody getting getting passed over for the Nobel Prize in a very similar situation. Can we think of in biology, who's that figure? You don't remember her name? Who remembers her name? Say it. You're close. You're getting it close. Do you know? Do you know who it was? Rosalind Franklin. What did Rosalind Franklin do? Do you remember?
Something 51.
Ah, photo 51. That's right. Very good. That's very good. Do you know what it was?
No, it's about something else.
Okay, well, hold on. What is it, James? What was photo 51? She discovered the structure of DNA, specifically that it's a double helix. So she was doing all this work with its X-ray crystallography is what it is. So she was doing all this work with X-ray crystallography, and she got one of her students, one of her like interns, actually got a photo of a DNA molecule kind of from above looking down, and you could see suddenly that it's a double helix. Who got the Nobel Prize for it? Watson and Crick. Watson and Crick got the Nobel Prize for it, and there was another dude in between who was literally a spy, like literally went and got her information. And the reason they got it, the stated reason that they got it was that they wrote their paper, which really they didn't have the data for without the information they got from their spy that talked to her. They published right ahead of her, which made it look like she was quoting their research when in fact they were quoting hers. And so she spent her life working in X-ray crystallography. Does anybody remember how she died? How would you die? What would do it if you spent, yeah, go ahead, BJ. Radiation. Spend your life in radiation. What are you going to get?
Radiation poisoning.
She got cancer. And just like a double whammy, I'm pretty sure it was ovarian cancer. So let's just like, no Nobel for you, and you get no ovarian cancer. So this one is, go ahead.
When you were saying, but talk about the illustrations and vectors, because the length was the magnitude and then the direction was the way it was.
There you go. That's right. You did catch a vector in there, right? So this is a good one about kind of encapsulates the two things he was saying, but why the weak nuclear force is ruining physics. I like the title too, why ruining physics, weak nuclear force.
The weak nuclear force gets short shrift among the four fundamental forces of nature. People wax on about the marvels of gravity that holds entire worlds together. They'll detail electromagnetism, which lets us see and keeps us from falling through the floor. They'll even praise the strong nuclear force that fights to keep nuclei together. Then they'll say the weak nuclear force causes radioactivity and fusion and then move on, which is a real shame, because the weak force has been causing trouble for a century, ruining everything physicists thought was true. And at the same time, it might be responsible for your very existence. Fundamentally, the weak force acts on leptons, which include electrons, neutrinos, and their heavier cousins, and on the quarks that make up particles like protons and neutrons.
Strange. I like it.
Changes a particle's identity by altering some of its properties. But other forces change particle types too, so that isn't what makes the weak force special. It's special because it's the exception to almost every rule. It's the Mongols of the forces. Hinton's trouble came around 1900 when scientists thought atoms of elements were conserved. For example, they thought lead atoms were lead atoms no matter how they moved or bonded, and the same went for every other element. Then they discovered radioactive decays. Atoms of one element can transform into atoms of another just by shooting some stuff out of their nuclei. Nobody knew it at the time, but this alchemy was the result of the weak force. And that wasn't the last time it overturned scientific common sense. The weak force also majorly messes with our ideas about symmetries, which help guide working physicists. These are things you might change about an experiment without changing the results of it. Like if I'm in front of an experiment and you're behind it, we shouldn't get different results. Physics should just care that something is moving, not that your left is the same as my right. Physicists in the early 1900s also figured that swapping left for right is no different from swapping up and down. You just turn your head or from swapping forward and backward. If all of those are symmetries, then swapping all three of them at once should be too. This is known as p-symmetry to the cool kids and parity symmetry to the rest of us. And it says that if you flip all these directions, no experiment will act differently. Experiments show that gravity would work the same way, and so would electromagnetism and the strong nuclear force, making a good case for p-symmetry being true. But the weak force to be different. See, particles have a property called spin. It's more complicated than the direction they're really spinning, but it's an okay mental picture to have here. One of p-symmetry's consequences would be that if something with spin decays, particles should fly out of it in a random direction. But in 1957, physicists watching cobalt nuclei decay reported that the direction of those decay particles depended on whether the cobalt spun clockwise or counterclockwise. And since the weak force causes decays, that meant the weak force is the only thing in the universe we've ever seen violate p-symmetry. Later experiments showed that spin really matters too. The weak force only acts on clockwise spinning matter particles and counterclockwise antimatter ones. That also makes it the only force that treats matter and antimatter any differently. So it's the only one that violates another symmetry called charge conjugation, or C-symmetry. And in case you were curious, it violates both of them at once too, known as CP symmetry. Much more recent experiments have also revealed that the weak force is the only one violating T, or time reversal symmetry. Gravitational, electromagnetic, and strong nuclear effects would all look exactly the same if time ran backwards, which is weird to think about. There are particles called B0 mesons that throw a wrench in things. They can exist in two forms, called B0 and anti-B0, and the weak force can freely switch a particle between forms over time. Switching in either direction should be the same, but switching from B0 to anti-B0 actually takes longer than going the other direction. The weak force's effects are therefore the only ones that depend on the direction of time, too. Today's physicists have retreated one more time to CPT symmetry, a combination of all three. Special relativity and the standard model of particle physics, two of the best tested ideas humanity has ever had, would both fall to pieces if it didn't work. And finally, so far at least, there's never been a single experiment violating it. Although we are looking. Now you might be wondering, so what? Why does it matter if one force is different and doesn't follow physicists' made-up rules? Well, for one thing, we want to know how all these forces are related to each other. That's like a particle physicist's whole job. Symmetries and conservation laws are also two of the most effective tools we've ever found to guide us to new ideas. If one force keeps being a weirdo, it makes understanding how the world works a lot harder. But there is another reason you might care. You could exist thanks to that CP symmetry violation. One of the big problems in modern physics is called the matter-antimatter asymmetry. Every reaction we've ever seen produces equal amounts of matter and antimatter. But the Big Bang made more of one than the other, because otherwise all of the matter would have collided with antimatter and annihilated into nothing. Of everything in the known universe, the weak force is the only one that seems to differentiate between matter and antimatter. So some modern scientists think that the weak force caused that asymmetry. It may have resulted in about one extra matter particle per billion particles. And that's all it took to make everything. Nobody has worked out exactly how yet, but the weak force is the only game in town, at least among ideas with solid experimental evidence. So it might not just be a pain in the metaphorical physics plot. The weak nuclear force could also be the reason the universe has anything in it at all. Thanks for watching this episode of SciShow. We hope you're okay after that. We love searching for the weird, eye-opening, and downright amazing stuff in the universe, but we would love to hear what you want to learn about.
You're okay after that.
An idea for a video.
That's excellent because, yike, right? So it's interesting, right? It's highly involved. You get into particle physics, nuclear physics, and all this stuff gets very, very complex. So if that's the kind of thing that you're interested in, and you're like, dude, this would be fun, I want to go work in a physics lab somewhere, then you definitely want to look into an AP or a dual enrollment physics class, and you want to look at universities that have engineering and good physics programs, and there's all kinds of stuff you can do within that realm. So there's never going to be like a lack of jobs, I don't imagine. So yes.
If you look inside my head, you will no longer find a brain, you will find an extra.
We'll try to look through as many of your
A big pile of mush because that was all crazy. So his quote is, and I looked it up. I'm like, what are Chewbacca's lines? What do they actually say? Because I'm sure there was some. That's actually what they write when they do a Chewbacca line. Yeah, I like that. That's in the script. There you go.
Cross between like a walrus, a badger, and something else.
That's the cutest little chewy rat ever. All right, so gravitational force. All right, Newton's law of universal gravitation states that every object in the universe is attracted to every other. So this is what force, Milo? Yeah, gravitational, that's where we are. So gravitational force is the attractive force that acts between any two masses. Bailey, are you attracted to PJ at the moment? Yep, you are. You're attracted. Yep. How about James and Chloe? Zoop. Yes, there you go. All right. But how about Drew and the cutting board? Yep. All right. Any two objects, you and anything else, me and the coins in my hand, any two objects. And the bigger the object, the stronger the force. You remember with the dude with the spandex where he said there's actually a spandex.com, which still amazed me. And he's rolling the marbles around. And you remember you would see one like orbit another and they would get together because they're being pulled together as they bend. Space-time, very complex, but really cool still. So gravity acts over large distances. It is the what?
It is the weakest. Like the weakest.
Mm-hmm. Yes, so it is the weakest, but it's the most effective over large distances. It's also probably the most obvious. That one and electromagnetic. I mean, truly, electromagnetic is obvious because, you know, if your eyeballs are open right now and you're physically able to see, everything you're seeing in here is because of the electromagnetic force, right? Because there is a visible spectrum and light is bouncing off things and reflecting back a different wavelength to us and we get color, right? So you don't think about that one as much, but it's constantly, plus, you know, we've got radio waves and microwaves and all of that. But then gravity is super obvious because, you know, you're not floating off your chair back there, Milo, or whatever. So yeah, gravity is like super obvious, but it's the weakest. To us, it's really strong, right? Like if you jump, you're getting sucked back down. If you slip on the ice, you're falling, right? So to us, it seems like a very strong force because anybody who's ever had gravity work against them, yeah, you know, if you've ever fallen down and busted your rear end or sprained your ankle or whatever, you know that it's strong in that respect, but overall it's not. All right, so here's our friend we've been looking at in rat form for a few weeks. You got to give Newton some props.
Welcome back to our series on the 4 fundamental principles of physics. Today we're talking about gravitation, the force that you and I probably have the closest working relationship with. But it's not only what sticks you to the ground and makes you fall down, it also explains how stars and galaxies form, and it will describe how they die. But even though we can watch it in action, gravitation is much more complicated than it appears. Generally, I think of gravitation in two different ways. The way that Isaac Newton described it, and the way that Albert Einstein described it. In classical Newtonian terms, gravitation attracts everything in the universe that has mass to everything else in the universe that has mass. And I mean everything from tiny particles to galaxies. It's universal and treats everything the same. But the strength of this attraction depends on the object's masses and the distance between them. The more massive an object, the greater the gravitational force it exerts on another, and the force decreases rapidly the farther apart the two objects are. Isaac described it this way: the force of gravitation is proportional to the product of the object's masses and inversely proportional to the square of the distance between them. Newton's mass and distance-based understanding of gravitation is really useful for stuff like predicting the existence of Uranus based on the movement of Neptune, but it doesn't explain everything, like Mercury's orbit. Trouble with Mercury is that the point where it's closest to the sun, its perihelion, isn't where Newton's law predicts. It took an Einstein to explain that. Actually, it took Albert Einstein. Einstein described gravity as a property not just of mass, but also of space and time. He envisioned space-time as the fabric of the universe, and his theory of general relativity basically says that objects that either have mass or energy distort that fabric. Think of a watermelon and an orange on a mattress. Each makes a depression in the mattress, and if the orange rolls toward the watermelon, it will accelerate as it reaches the depression made by the more massive fruit. The attractive force doth get weaker or stronger in the distance between the fruits. It's like Newton's law on steroids. Gravitation is the warp in space-time created by mass or energy. So in the case of Mercury, the closer it gets to the sun, the more the sun's huge mass curves space-time, which effectively causes that point of perihelion to move. You'll notice that this applies to objects with mass or energy. Einstein discovered that gravitation can also influence energetic but massless stuff like light if the force is strong enough. For instance, he observed that light bends around really massive planets and stars, and his theory of general relativity predicts correctly that a compact enough mass could distort space-time so much that light could not escape it. And that is a black hole. Now remember that for each fundamental force, there is a particle, a force carrier that essentially conveys force between bodies. But if light responds to gravitation, its force carrier must be really tiny. Gravitation is described as being carried by massless photons. But
There you go.
unlike other force carriers we've talked about, like pions and gluons, gravitons are theoretical. They've never been detected, and they are predicted to be essentially unobservable. We're only able to witness their handiwork, and that is gravitation. We hope that you enjoyed our series on the 4 fundamental forces of physics. If you or in the YouTube comments below. Goodbye.
Laws on steroids.
So yeah, so what's the difference between Newton's model of gravity and Einstein's model of gravity? Okay, Colin,
One of them was created by Newton, one of them was created by Einstein.
that's part it. All right, Yusuf.
Newton only considered mass, Albert Einstein also considered energy.
Yes, mass and energy. And Newton's was pretty much just every object is attracted to every other object, period, right? But Einstein talked about space-time, right? He got into the whole space-time thing and how it can be warped. So you can think of that mattress, or you can think of that big spread out piece of spandex that dude had over that giant hoop. And he, he would put that weight. Remember, he looked like a hockey puck. He put that down and it pulled the fabric. And then when he released the little balls, they would kind of go around it and they'd get more attracted to it. And you'd have like a smaller mass and then a bigger mass. And you could watch how it was attracted, because that bigger mass is bending space-time and creating a curve in the path. So it is kind of like Newton's on steroids. We've added another layer. Y'all okay back there? Y'all giggling away. Gigglers. All right, so gravitational force, Earth, moon, and tides. So what's this one here, Bailey? Okay, centripetal. So this is an interesting one. So there will be arguments, as you'll see, that it's not really even a thing. It's just an observation of another thing. But centripetal force is your center directed force that constantly changes the direction of an object, causing it to move in a circle. So satellites in orbit. And a satellite doesn't have to be a man-made thing. Like the moon is a satellite, right? And are you good back there? And certain planets have lots of moons, so they have lots of satellites, right? So what keeps a satellite in orbit is centripetal force versus what? Caitlin.
Oh, I put down those rockets. That's
Rockets are good. Let's see. I have Chloe and Liam and Ridley who haven't answered yet. Either any of you want to guess, Chloe? Yeah, there you go. So it's centripetal force versus gravity that keep it in motion. All right. So that's what keeps them orbiting, because their centripetal force is pulling them in the circular path, kind of like away from Earth, if you think about the moon. But gravity is constantly pulling the moon towards us, right? And we learned before about tides and what causes tides. So if we had a high tide, if we were at the ocean in I don't know, say we're down in like Beaufort, South Carolina, or that area, Savannah area, where they have a lot of marshland. Now it's high tide. What does that tell you about the moon, PJ? The what? Oh, yeah, the moon is closer at that point. It's closer at that point, and it's pulling that water towards it. So on the opposite end of the Earth, what's happening there? Let's see, either Liam or who else is it? Ridley. Ridley, what do you think? Yeah, yeah, the other side's getting a low tide, because the water's being pulled this way. Or this way, or wherever the moon is closest to. Okay, so this is gonna summarize all four of these. Now we've looked at, I know there's a lot of videos in this one, but because there's a very short lesson, so I'm trying to make sure that like we get a little more in depth and some examples that you can actually see instead of just blah, blah, blah. So
This video is sponsored by Great Courses Plus.
that's great, by the way.
Imagine taking
Those
a
are cool.
notebook, a plastic bottle, a toaster, and a glass container and burning them in a fire. If the fire was hot enough, all the materials in these four things would break down into a gaseous mixture of molecules and atoms. If you make this fire hotter, all the atoms would break down into the component electrons and neutrons. If you go hotter still, these particles break down into the fundamental particles of the standard model, things like quarks and leptons. And if you go even hotter, we're talking astronomical temperatures, about 10 to the 31 degrees, or about 1,000,000 trillion degrees Celsius. All the quarks and leptons, the four fundamental forces of nature, would break down into one entity, kind of soup, where all the fundamental particles and the underlying forces responsible for their behavior would meld into one. This is what is believed to have existed at the moment of creation, at the moment of the Big Bang. All the particles and forces of our reality came from this primordial soup. But this is the story of the four fundamental forces of the universe that as far as is known, control everything in the universe, every movement, every phenomenon, and every process you can possibly think of. What is the nature of these forces? How do they work? And where did they come from? That's coming up right now.
We like simple answers, right?
Theory represented by the standard model of particle physics. All matter is composed of 6 quarks and 6 leptons and their 12 antiparticle pairs. But that's not all. Matter is subject to 4 fundamental forces that cause this matter to behave in certain ways and result in essentially every action that you see all around you and everywhere in the universe. These 4 forces are the strong force, which binds the nuclei of atoms by holding protons and neutrons together in their center. The weak force, which is responsible for some kinds of radioactivity. Electromagnetism, responsible for electricity and light, and is also the root cause of chemistry. And finally, gravity, which binds us to the Earth and keeps the planets in their orbits around the sun. Yet the most interesting aspect of this picture is that at a fundamental level, scientists believe that all the forces come from one underlying force or principle. And astonishingly, not only that, but according to current understanding, all 24 of the different fundamental particles and the 4 forces are one and the same at some deep level. This is the ultimate symmetry of the universe. Perhaps the best way to understand this and how these forces emerge is to visualize what happened at the very beginning of time, at the Big Bang, when everything was one. Time began not at 0, but at the smallest measurement of time that can be represented by our models of quantum mechanics, and that is Planck time. This is not 0, but pretty close from our perspective, 10 to the negative 43 seconds. This is not to say that nothing existed prior to this, but it is just the limit of our knowledge. We are ignorant of anything that might have occurred prior to this first epoch of existence. So this is aptly called the Planck effect. All the forces and particles were one and the same, in a point smaller than the size of a proton. Gravity is thought to have separated from everything else shortly after this time period. So it was the first force to separate out from the other 3 forces. The temperatures at this stage of the universe were, as you might expect, astronomical, 10 to the 31 degrees Celsius. And the energies were on the range of 10 to the 19 billion electron volts or giga electron volts. If we ever develop a theory of everything, then it would explain everything that occurred up to this time. The strings of string theory and the loops of loop quantum gravity, if those theories are correct, come into existence and apply here. The next era, called the Grand Unified Epoch, lasts from the first Planck second, 10 to the negative 43 seconds, to about 10 to the negative 35 seconds. Up to this period, the remaining 3 forces, the strong force, the weak force, and electromagnetism, were all united. But shortly after this period, from about 10 to the negative 34 to 10 to the negative 32 seconds, the strong force separated from the other 2, electromagnetism and the weak force, which were united as one force called the electroweak force. Temperatures were now around 10 to the 26 degrees Celsius, and the energy was reduced to 10 to the 15 giga-electron volts. If we ever discover the grand unified theory or gut, which unites the strong force with the electroweak force, we would need to model what happens at these energy levels and temperatures. Somehow, this separation of the strong force is thought to have resulted or powered something called cosmic inflation. This is the momentary expansion of the universe, which went from something tinier than the size of a proton to the size of a grapefruit. This is a huge increase in size. It's analogous to something as small as a tennis ball becoming the size of the solar system in a very small instant. At 10 to the negative 12 seconds, called the quark effect, the electroweak force split into the weak force and electromagnetism. These two now became separate forces. So at this point, all the four forces became distinct. The temperature of the universe cooled to 10 to the 15 degrees Celsius, and energies are about 100 giga-electron volts. We know a lot about the universe up to this era because such energy levels can be easily modeled in particle accelerators.
That thing is
large
cool.
collider. So our understanding of the electroweak force is fairly robust. The Higgs field also exists at this stage as well. How do we know? Because about 100 giga-electron volts was needed to create the Higgs boson, and this can be done at the LHC. Now, fast forward to today, 13.8 billion years later, where the average temperature of the universe is negative 270 degrees Celsius, and energy is on the order of 0.25 electron volts. Let's look closer at the four forces, and let's start with the two we are most familiar with, gravity and electromagnetism. They are similar in that their mathematical formulas look nearly identical. Newton's law of universal gravitation can be expressed as the following, where G is Newton's gravitational constant. Coulomb's law of electrical force between charged bodies can be expressed as the following, where K is Coulomb's constant. The first formula tells us the gravitational force between any two bodies is proportional to the product of their masses and inversely proportional to the distance between them squared. Notice that the force extends infinitely far. This means that the Earth has a gravitational effect on not just the moon and the other planets of our solar system, but also some effect on every other massive object in the universe. Mind you, this is a very small effect because the R in the equation would be very large for things very far away. So the force would be very weak, but it is non-zero. And since gravity affects anything with mass, this effect is the most influential force on a cosmic scale. But almost everything I just said also applies to electromagnetism. The electrostatic force between charges extends also infinitely far away. This means that a charged particle on Earth has a non-zero effect on a charged particle near Proxima Centauri, our nearest neighboring star, and charged particles everywhere else in the universe. And this force is much, much greater than the force of gravity. In fact, the magnitude of electromagnetism is 10 to the 36 times greater than the magnitude of gravity. So why isn't electromagnetism the most dominant force in the universe? The reason is because on large scales, electric charges of large objects tend to cancel each other out. Large objects tend to be neutral. So since a charged particle can only affect other charged particles, this force is mostly non-existent at large scales. If large things were not electrically neutral, this force would completely dominate our universe. But electromagnetism still has a big influence in our world. It is responsible for the nature of light, and it is the main force responsible for all the biochemistry taking place in our bodies and the rest of Earth. It's the basis of all chemistry. So now you have to ask, if electromagnetism is so strong, then what keeps multiple protons, each of which are positively charged, bound in the nucleus of atoms? According to Coulomb's law, if you do the calculations, the two protons of a helium atom experience a force equal to about 20 pounds. For something as small as atoms, this is a huge force. They should repel each other and fly apart instantly. The reason that protons don't fly apart is because they are kept glued together with a force that is even stronger than electromagnetism, 100 times stronger. And this force is creatively called the strong nuclear force. It is the strongest force in the universe. However, it extends only as far as the width of a proton. Remarkably, it is very small or non-existent beyond this line. This force has been described as Velcro. When two protons are really close, the force keeps them strongly bound together. But when they are further apart in the width of a proton, it's about non-existent. This force is not simply the opposite of electromagnetism, though, because it is also responsible for holding electrically neutral neutrons in the center of atoms as well. Even though this is a force we can't directly experience, the world has experienced its effect. How? Because, as you see, the release of this force is the energy behind nuclear bombs. The fission and fusion of atoms releases huge amounts of binding energy from the nucleus of atoms, which results from the strong force. The binding energy of this force, in fact,
Yo, dude.
not the Higgs field, as you might have thought. And when this binding energy is released, mass of the atom is converted to energy in nuclear reactions. Then we get to the weak force. This is responsible for a type of radiation called beta radiation, which is the emission of electrons or its antimatter equivalent, positrons. One of the most important processes in nature is the beta decay of a neutron. This happens, for example, when a neutron decays into a proton, an electron, and an antineutrino. If this kind of decay had not occurred, then the universe would have been awash in a sea of neutrons, and no atoms would have ever formed, and we would not have had life. This process is also important in making larger atoms stable because a similar decay called beta plus decay occurs when a proton is converted into a neutron, a positron, and an electron neutrino. It results in positron emissions, and this process allows for nuclear stability. Like the strong force, this force is also only effective at really small scale, but the range is even shorter than the strong force. Its effective length is only about 1,000th the diameter of a proton. Now, I've tried to give you an overall perspective on the four fundamental forces, but if you're like me, you probably have a few questions. First, you might ask, how exactly does a force between particles work? What is the underlying mechanism? What causes an attraction or repulsion? And why does electromagnetism and gravity have an infinite range, but the strong and weak force have such a small range? The answer to these questions are closely related, and to get into some of the most cutting edge and complex science involving quantum mechanics and particle physics. And this will be the subject of my next video. So
Y'all welcome to watch that one.
In the meantime, I'd like to thank the sponsor of today's video.
Yeah. So the big points here are that the strong nuclear force is the strongest, but how far does it go? What's the range of a strong nuclear force, Xander?
The width of a proton.
The width of a proton. Okay. So if in the middle of an atom, you got a bunch of protons packed in there together, they're all positively charged, they should be pushing away. Have you ever thought of that before? You have a bunch of positively charged things in the middle of an atom. How do they stay there? Because positive and positive should repel, right? So when you think about it, it doesn't make any sense. They shouldn't be there. They should be pushing away from each other, but they stay because of strong nuclear force. But it's only the width of the proton. So it's the strongest force we have. It's universal, but it's itty bitty. And the long range forces like electromagnetism and gravity are much weaker, but they're farther. They have a better range. The range is farther. So like Earth has some sort of impact on Jupiter, and Jupiter has some sort of impact on Earth. But then you get this itty super strong force that is keeping your atoms together. And when you split an atom, what is it called? Yeah, it makes an explosion. But what's it called when you split an atom? What's the process? Do you know?
Nuclear fission.
Yeah, it's nuclear fission. That's what we're looking for. And what is it called when you combine atoms to make a new atom? Yeah, PJ. Fusion, right. Okay, so they showed that, you see that it was like a map and there was a circle? Okay, do you know what that is? He touched it briefly, and if you hadn't already heard about it, you might not know. So that is called CERN, C-E-R-N, and it is a particle accelerator. It's a massive loop, and they will put heavy elements in there, atoms of heavy elements, and spin them super hard because they're trying to get them to collide together and create a new element, which they can do. The problem is it's so unstable, it's an instantaneous existence. It's there and it's gone. There and it's gone, poof. But they can actually do it. They can accelerate them so fast that the result is you got something new, but it doesn't last long. So this guy also took what we've always thought of as the instantaneous Big Bang, right? The instant, and broke it down into like, 10 times something to the 10 to the negative 35th. I mean, you're talking faster than we can conceive. And they've broken that down into phases. And this is particle physics, man. They broke it down into phases in order to describe the Big Bang. And they believe they know in which order these forces separated out, because they believe they were all one and the same at the beginning. So that's the idea, is all in all. Yo, dude, I got you. Go ahead. Move on. Yo. Oh, I love it when they just don't go away. Okay, so this was like, hang on, don't start. You always start scrambling. So yeah, like I said, it's a shorter lesson because we didn't cover as much stuff, but some of it was really, really deep stuff. Now, when it comes to what you'll be responsible for, I want you to know what the 4 universal forces are. I want you to know what the strong ones are versus the weak ones. And I want you to be able to explain like how they're acting. It would be good for you to be able to say, okay, the weak nuclear force is seen inside of an atom versus, I mean, you could break it down that little, you'd get some partial credit for that. Strong nuclear force is why protons can stay together in a nucleus, right? Gravity is any 2 objects attracted to one another, right? Okay, so what I'm going to ask you to do, because you have about 16 minutes, is I'm going to ask you to take a minute to help clean up from lab. If it is something that is not trash, like a ruler or a car or a marble or a whatever, I'll ask that we're going to leave this little box that I created up here with the rulers and the dowels. We're going to leave that little box. Anything that isn't trash, please put in the little box. Anything that is trash, please put in the trash. So like the string and stuff can go in the trash. All the balloons, because y'all touched them, they can all be trash. Hey, Liam, what do you like on your pizza? You're the only person who didn't answer a question. What do you like on your pizza? All right, there you go. So, make everybody answer something at least once.
Even if my answer was rocket, I still got.
You still said something. That matters. Yeah. There you go. I don't remember. Something. There you go. No, there's that though.
Good.
Yeah.
Would you like to see my family cranes?
I love those. So I actually, years ago when I was teaching at my private school, I did a theater class after school, like a extracurricular theater class. And we did a play called Amma and the White Crane. And it's based on a true